Good day, everyone. I am Joseph of Digilitic Solutions. I am a consultant, trainer, speaker, and a book author. Welcome to our course, Mastering Machine Learning Algorithm. In this lesson, we will learn about analyzing density function. At the end of the lesson, you are expected to identify the density function of continuous random variables, define the joint and conditional densities, and appreciate the density function in the context of machine learning. In our last session, we learned about how to define probabilities in Python. We learned what packages to install to do our data science projects. We learned about data science and Prob 140. We learned how to construct joint distributions by calling the dot probability function. Also, we were taught how to do marginal distribution by calling the dot marginal function. Lastly, we were able to construct conditional distributions. This can be done by calling the method conditionalDist. If you missed lesson 7, the link is given in the description below. You may pause this video and come back if you are done with it. So unlike the idea of discrete random variables, wherein the possible values of different outcomes can be mapped out, we cannot systematically write them in the case of continuous random variable. So this kind of property really stops us from assigning probabilities to a particular value. So at this instance, maybe you would like to ask me, are we left helpless? Don't we have any possible options for us to assign probabilities to a particular value? Well, of course, we are not left helpless. So our remedy here is to work with the outcome within some range or interval. So let me write range or interval. So we will not forget range or interval. So again, our remedy here is to work with the outcome within some range or interval. So what this means is that, for example, considering this one, let's have this equation. So what this means is that, for example, considering a random variable x, okay, so we have here x, which can have any value between minus infinity and infinity. So we can do the probability of x within minus infinity to infinity. So x1 here and x2 here are actually the points of interval from the lowest to the smallest, the lowest to the highest. So this is the negative infinity and the infinity. Why negative? The negative here means that it is the beginning or the lowest interval, the lowest point in the interval, and here is the highest point in the interval. Okay, so anyway, these and these are just the same. So, but we cannot do this for p x equals x. The reason is that it is continuous and the discrete value of x cannot be found. Let me repeat that. We cannot do this for x equals x because the reason is that it is continuous and the discrete values of x cannot be found. Again, we're talking here of a continuous random variable, and identifying the exact value of x cannot be made possible in this case. And it cannot be found. So for us to compute the probability that x can be found in a certain range, so in this case, for example, x1 to x2, we're going to compute a definite integral with respect to x over this range. So this definite integral from x1 to x2 of px and dx. So what's the meaning of this? So this means that px, which can be bigger or higher or equal to 0. Px can be greater than or equal to 0. So still remember our lesson in lesson 3. So this is actually the equivalent equation. So what's the meaning of this equation? So what does it tell? So this tells us that a PDF cannot be negative. Why? Because x here is obviously greater than 0. And what is greater than 0 starts from 1, or even 0.0001. The striking property of PDF as shown in this equation is that there is no upper bound on PDF value. So it means that it can be higher than 1 for a particular value of x. Okay, so this time, let's talk about joint and conditional continuous densities. So are you thinking if we can define their density function? Of course we can. Just like discrete cases, we can also define the PDF or probability density function over many continuous random variables. So for example, let's start first with this one. Okay, let's number so we won't get lost later. So this is 1 and then this is 2. So we have the probability of x and y. So I would like to point out that this is the case of a joint distributions. So this is a joint density of two random variables x and y. So of course, we cannot compute px. Let me write that px equals to x, y equals to y. Okay, but we can compute within what range or interval? Again, because we cannot compute this because this really calls for the exact value. And in the case of continuous random variable, we cannot get the exact value of x or y. So we have this statement. Okay, anyway, we can compute within what range or interval. So even if we cannot compute the exact value, we can actually compute within what range or interval. So we have the statement to get the outcome. So this one. So we have the probability of x that can be found in the interval x1 to x2 and y, which can be found in the interval between y1 and y2, which is equal to the definite integral from x1 to x2 multiplied to the definite integral from y1 to y2, then px y dx dy. Okay, so as to the conditional distributions, like this, or as to the conditional distribution, the same applies, but of course with condition. So again, this is joint and this is conditional. So if you're going to examine closely, the same process applies, but only that in this case there is a condition. So if you still remember our lessons about conditional distribution, so we learned that there is a condition that affects the probability of the second, the third, or the fourth events, depending on how many events you have in your problem. So in this case, we can describe the density function of x given that y is small y. So let me write that. Okay, here. I think I need to use the black one. So we have P, okay, X, small y. Okay, so we have the probability of X given y. So transforming this statement into another statement for clarity, then we have this. So we have the probability of x1, which is less than or equal to x, which is less than or equal to x2. So again, this is what we call the interval, given that y is equal to the small y. So which is equal to the definite integral from x1 to x2 p x given y, which is equal to small y dx. So this is actually the shorthand expression. So here the condition is in the exact value. So again, our condition here is y. So y. So this is our condition. So this is the exact value. Okay. So maybe at this point you would like to ask me, why is it that there is an exact value? Thinking that a while ago we said that a discrete value cannot be found in continuous random variable, right? I think that kind of question is very senseful. Okay, so well, the answer is simple. The exact value because, or there is an exact value of y here because this is the event that is assumed to have already happened, because y is assumed to have already happened, so it means that we already have the value. So that's why in this case the given value of y is exact. Okay, makes sense? Okay, so and lastly, as to marginalization, very simply we are just going to replace the summation from discrete case with an integral. For example, we have this statement. So still remember the summation of the discrete random variable. So remember that symbol. So if we're talking about continuous random variable, we just replace this notation with this, the integral notation, or definite integral symbol or integral symbol. So that means the probability of y is equal to the definite integral from x1 to x2 p y x dx. So here the interval of x1 to x2 describes the sample space of x. What is this for? Why do we have to study this? If we know the probability distribution, we can calculate its descriptive characteristics like mean and variance. Also, this can help us detect likely or unlikely observations, which can be an anomaly or an outlier. After all being said and done, let's try this. What is a probability density function? How do we get joint and conditional densities? And lastly, what are some of the uses of density function in machine learning? Do not forget to subscribe, like, and share. Please click the bell button to be notified every time we have a new session. See you in the next lesson.